Okay, let's start this lecture with the example that we were considering in the previous class. So we have a domain. We have taken a square domain for simplicity, and in this domain we have this mesh of triangles. Okay, let's number the elements and the nodes of the mesh. This is node 1, this is node 2, this is node 3, node 4, 5, 6, 7, 8, and then 9. Elements, this is my element 1, this is element 2, this is 3, 4, 5, 7 and 8. So this mesh has 8 elements and 9 nodes, and you see the way I have drawn, it's a square mesh. All the elements have the same shape, and what we have, let's take further that the edge, straight edges of the elements are of size h. So both the straight edges of a given element are of size h. That is, my domain is of size 2h by 2h. For this domain, I would like to do the element stiffness matrix calculations using the linear approximation over the domain. So let's go through the steps that we have done earlier. So let's take element 1 as an example. Element 1 is this. Okay, so if I look at the coordinates of element 1, let's say my coordinate system that I have employed is like this. This is the origin O, this is the x-axis, this is the y-axis. So the coordinates of the n nodes of the element 1 are 0, 0, h 0 and h h. And remember that the first one is a global node 1, the second one is a global node 2, and the third one is a global node 3. And I want to give now a local numbering to the nodes. So local numbering is, this is my local 1, this is my local 2, this is my local 3. That is for the element, this first node, this is the first node, this is the second node, this is the third node, and they correspond to the global numbers. That 1 is equivalent to the global 1, 2 is equivalent to the global 2, and 3 is equivalent to the global 5. Okay. So given this, now I can write what is my x using what we have done. X is equal to x1 n1. Okay, x1 n1 in the master this thing representation. So x1 is 0, n1 doesn't matter. So 0 plus x2 n2. So h into x2 and what is n2? N2 is psi plus x3 n3. What is x3? It is h into, and what is n3? It is eta. Similarly, y is equal to y1, which is 0, plus y2 n2, y2 is 0 into psi, okay, plus y3, which is h into eta. So these are my representations of x and y. Okay. So given this representation of x and y, now I can easily find what is del x del psi equal to, del x del psi is equal to h, del x del eta is equal to h, del y del psi is equal to 0, because y is not a function of psi, del y del eta is equal to h. I am simply using my representation of the x and y. So for the first element, this is my element 1, remember. For this element, these are the del x, del psi, etc. I get. So if you remember, our Jacobian matrix becomes essentially del x del psi from the previous one which is h, del x del eta, which is h. So it is h, this is h, this is 0, this is h. This is equal to the Jacobian matrix. Implies the Jacobian itself is equal to h squared. So this is what I get as my Jacobian. Okay, next is if I get this Jacobian, then I would like to now get the matrix of the inverse transformation. So if you remember that the inverse transformation will have J inverse is equal to 1 by Jacobian into del y del eta del x del psi minus del x del eta minus del y del psi. So this is equal to 1 by h squared into, I take these two guys, invert them, this guy, so it remains h, and take the negative of the off diagonal terms. So implies del psi del x is equal to 1 by h, del psi del y is equal to minus 1 by h, del eta del x is equal to 0, del eta del y is equal to 1 by h. Okay, so given these matrix of the inverse transformation, now we are in a position to find the x and y derivatives of the shape functions. So if I want to find the x and y derivatives of the shape functions, so we have del n1 del x is equal to del 1 hat n1 hat del psi del x plus del n1 hat del eta del x. Now n1 was 1 minus psi minus eta, so if I write it, so del n1 del psi would be 1 minus 1, so it's minus 1 into del psi del x. Del psi del x from the previous page is 1 by h, 1 by h, plus del n1 del eta, which is minus 1, into del eta del x. Del eta del x is 0. So this becomes minus 1 by h. Similarly, del n1 del y would be equal to del n1 hat del psi del y plus del n1 hat del eta del y. Now this will be equal to again minus 1 into, if I go, del psi del y is equal to minus 1 by h. So it is going to be minus 1 by h plus this quantity is minus 1, del eta del y for us is 1 by h, so it's 1 by h. So this becomes plus 1 by h minus 1 by h, which is 0. So if I look back, let's go back and look at the element. Does it make sense? If you look at the first shape function and I want to get it in terms of x and y, it turns out this shape function will be nothing but 1 minus x by h. So because it has to have a value 1 at x equal to 0, so it is 1. It has a value 0 at x equal to h. So if it is in the physical element, it is 1 minus x by h. So del n1 del x is equal to minus 1 by h, and del n1 del y has to be 0, and that's exactly what we got out of our transformations. Okay. Similarly, I can have del n2 del x is equal to again del n2 del psi, which is del n2 del psi, because n2 is psi, is 1 into del psi del x is 1 by h, plus del n2 del eta, which is 0 because n2 is del n2 hat del eta, because n2 hat is psi, and this is del eta del x. So this is going to be 1 by h. Del n2 del y is equal to again del n2 del psi, which is 1 into del psi del y, which is minus 1 by h, plus del n2 del eta, which is 0 into 1 by h, which doesn't matter. So this is minus 1 by h. Del n3 del y del x is equal to del n3 del psi, where del n3 del psi is actually 0 because n3 is eta. Okay, so we have del n3 del psi, which is 0, del psi del x, which is 1 by h, plus del n3 del eta, which is 1 into del eta del x, 0. So this is going to be 0. Del n3 del y is equal to 0 into del eta del y, which is minus 1 by h, minus 1 by h, plus del n3 del eta, which is 1 into del eta del y, which is 1 by h. So this becomes 1 by h. So I have these three quantities, and as we had said last time that let's take the very simple differential equation. We had taken the generalized differential equation, partial differential equation, in terms of one variable, which is u, with all these coefficients k11, k12. So what we are going to do is we are going to take the differential equation k11 is equal to 1, k12 is equal to k21 is equal to 0, and k22 is equal to 1. So using that differential equation, now we have the variational formulation. If you remember, over the whole domain omega will be given as del u del x into del v del x plus del u del y into del v del y dA is equal to integral over the omega, if there is a source term, RV dA, plus on the Neumann part of the boundary we will have GV ds, which is the boundary line or the contour. So this is our differential equation. So from this, as we have discussed many times, we are interested in the integral, the part of this integral on the right hand side and the left hand side coming from our particular element, and that integral is going to give us our stiffness matrix and the force vector terms. So let us take the element. So we will say for the element tau equal to 1, for the first element I will have del u Fe del x del v del x plus del u Fe del y del v del y. This integrated over dA will be somehow related to our stiffness matrix. So we know how to do it, because we said that in the element, if I have taken the first element, okay, the first element, if you remember, the active basis functions correspond to the degrees of freedom 1, 2 and 5, which correspond to the local 1, local 2, local 3. So if I write my UFE in the element in terms of the global phi 1, phi 2 and phi 5, because these are the only non-zero ones, V also in terms of the global phi 1, phi 2 and phi 5, which means my element only contributes to the global equations 1, global equation 2, global equation 5 and to the columns 1, 2 and 5 of the global equations. This is exactly the way we have discussed it for the 1D problem. Okay. So now, which means that from our previous representation, I will be only talking in terms of the ni's from the element, that is nj of the element tau, and instead of v I will be putting ni of the element tau, where the I and the j go from 1 to 3, because I have only 3 functions defining the linear in the element. So, okay, my element stiffness matrix then will be Kij for the element tau, which is here tau is equal to 1. This is equal to then integral over the element tau of del nj del x del ni del x plus del nj del y del ni del y dA. So I have to evaluate each of these entries, and this has to be a 3 by 3 matrix because I have only 3 unknowns in the element. So how do I evaluate these entries? Well, we have done most of the job. So I take this integral, map it to the master element, that is over tau hat, and I will have here del, I will retain these things, where I will understand that these derivatives are obtained with respect to the master coordinate system, into Jacobian into dA hat. Now this is equivalent, this integral is actually equivalent to writing an integral over, if you see in the master element, the way we have defined the master element, psi goes from 0 to 1 and eta also goes from 0 to 1. So if I take a strip here, look at this area of the strip, the equation of this line is equal to eta is equal to 1 minus psi, okay, and this line is essentially, this line is eta equal to 0. So then I can write the integral as psi going from 0 to 1 integral over eta going from, I am looking at the area of the strip, psi goes from 0 to 1, eta goes from 0 to 1 minus psi into whatever is my integrand into the Jacobian into d eta d psi. So this is the integral I am supposed to do. Okay, so for us the job is very easy, because if you see our derivatives del n1 del x del n1 del y del n2 del x del n2 del y and so on are all constants. So here we are simply integrating constants, okay, and the Jacobian is also constant. So our integral gives us, let's say I want to find k11 will be equal to integral over the psi integral over the eta of del n1 del x whole squared plus del n1 del y whole squared into Jacobian into d eta d psi. Okay, so for us this del n1 del x whole squared will be equal to del n1 del x is equal to minus 1 by h, del n1 del y is equal to 0. So let us put that, and Jacobian is equal to h squared. So let's put all those things in our expression. So k11 is equal to del n1 del x is equal to minus 1 by h, so 1 by h whole squared into the Jacobian, so integral, this comes out, Jacobian is also a constant, so this is h squared into integral over the area of the master element dA hat. So essentially this whole integral is nothing but area of the master element, but area of the master element has, the master element is a right angle triangle with sides of length 1, so area of the master element is half, so this becomes half. Okay. Similarly, I can find K12. K12 will be integral over the area, so del n2 del x del n1 del x plus del n2 del y del n1 del y into Jacobian into dA hat. Now for us, del n2 del x, if we compute, del n2 del x was equal to 1 by h. Okay, so this is equal to 1 by h. Del n1 del h is equal to minus 1 by h. Del n2 del y, if I look at it, it will be minus 1 by h. I get to minus, this guy will be minus 1 by h, and del n1 del y 0. So this quantity essentially becomes equal to minus 1 by h squared into the Jacobian h squared into the area of the master triangle is half. So this is minus half. Similarly, K13 will be equal to integral over a hat, again del n3 del x del n1 del x plus del n3 del y into del n1 del y into Jacobian into dA hat. Okay. So if I do this one, now I know what is this quantity, this is minus 1 by h, this quantity is 0, so del n3 del x is 0, this is 1 by h. So the whole integral actually, because integrand is 0, is equal to 0. Okay. I have these entries. Similarly, I can find what is K22. K22 will be integral over a hat of del n2 del x whole squared plus del n2 del y whole squared into Jacobian dA hat. Now this whole thing will become 2 by h squared, the sum, into h squared into half, which becomes 1. Okay. So if we do this exercise all the way through, then I will see that my K for the element 1 is equal to half minus half 0, and because the stiffness matrix is symmetric, so I don't have to compute all the terms, I can get them from symmetry. This is half, K22 was 1, and if we do the calculations, we'll find out that K23 is minus half. So this one will be 0, this is minus half, this is half. So you see that one thing you should see, that if I add the rows or the columns, all the terms in a row or all the terms in a column of the stiffness matrix, then I get 0, which tells me that the stiffness matrix is actually singular. Okay, it should be, because if I look at an element as the whole domain, then obviously the element should give me a singular stiffness matrix, because the global rigid modes are not constrained. What are the global rigid modes? That corresponds to the constant u. Okay, so we have to fix one value of u. In fact, the rank deficiency of this matrix is 1. Okay, this one can check out. So if I can find the element stiffness matrix for element 1, then similarly I can find the element stiffness matrices of elements 3, 5 and 7. Why? Because if I go to my first slide, you see that the first element, the third element, the fifth and the seventh have exactly the same geometry. Okay, exactly the same geometry. They are essentially the same triangles, just translated by some distance in the x direction or y direction. So the derivatives of the n1, n2, n3 in each of these elements will remain exactly the same as that I got in element 1. And because of those derivatives being the same, in fact the metrics of forward and inverse transformation will also be the same. So the stiffness matrices corresponding to the elements 1, 3, 5 and 7 will be identical. So these will have, so this will have identical to tau equal to 1 as far as the stiffness entries are concerned. If I take element 2 is like this, with the global nodes 1, 4 and 5. And if I write the, now I can do the local numbering for element 2 in such a way as this, that this is my local 1, this is my local 2 and this is my local 3. If I do that numbering, then I am actually following the numbering which I had done for element 1. So if I turn the element 1 around, okay, rotate it around, I will get exactly the local numbering as that I have done for element 2. Okay. If I do this numbering for element 2, then that is the local enumeration is completely up to me. The only thing I have to ensure is that the enumeration is done in a counterclockwise manner. I am always numbering the local numbers in a counterclockwise manner. So then for the element 2 also, you will see that k of 2 essentially equals k of 1. So in a way, now very easily I have been able to obtain for this simple problem that I have taken, this particular problem, the element stiffness matrices for all the elements concerned. Okay. So next we have to do the load vector calculations at the element level. Now when I am talking of the load vector calculations, then I have essentially I am talking of the integral of the element over the element of R into V dA plus the part of the Neumann boundary which intersects the edges of the element, okay, GV ds. Because this is something that we have to also take care of, that this is essentially due to the internal source term, okay, or you can think of it as the body force term, and this part is due to the boundary traction terms or the flux terms. And we have to see whether the element shares an edge, because the element has the 3 edges. I can define the 3 edges of the element, okay, that is in the master element. If I look, this is 1, 2 in the master element, this is 3. Then in the master element, I'll call this as my edge 1, this as my edge 2, this as my edge 3. So if I have an edge, the edge actually has the 2 extremities given by the 2 nodes sitting at the 2 ends. So edge is like a 1D element, and so for each edge I have the 2 nodes corresponding to the edge, and I can have either edge 1 or edge 2 or none of the edges lying on the boundary of the domain. And if it is lying on the boundary, I have to figure out whether it is common, it is actually on the Neumann boundary. If it is, then I have to apply the Neumann conditions there. So first we are going to talk about this part. Okay. Let's say that let R be equal to 1. Let's take a constant value of R, and we have taken R equal to 1. So at the element level again, which of the V's are non-zero? It is essentially the n1, n2, n3 of the element. So I'll have to do the integral over the element of 1 into ni tau dA. Okay, but this is equivalent to doing integral over the master element a hat of 1 into ni hat into Jacobian into dA hat. Now this Jacobian is a constant, so essentially this is equal to, for us it is h squared into integral over a hat of 1 into ni hat dA hat. Okay, if I do this integral, this is quite easy to do. If I do it with respect to psi or eta, you will see that these integrals will come out to be the same for each of these shape functions. Okay, remember this is true because we have taken r equal to a constant. So this is going to be equal to, actually the integral is going to come out to be h squared by 6. So I am now in a position to write the f for the element tau, and for the mesh that we have taken, for all the elements this f tau is going to be the same. This is, remember we are talking only of the part coming out of R. So f tau, maybe we will say R is equal to h squared by 6, h squared by 6, h squared by 6. Okay, let's go back. If instead of this r I had r as some function of x and y, then here I have to map this as a function of, it will be r hat of psi and eta. So this integral now has to be done piecewise, that is for each of the shape functions I have to find the integral. I cannot say now that the load vector term coming out of this integral is the same for each of these shape functions. This is one thing you should keep in mind. I have to do the explicit integration there. Okay, fine. So I have this coming out of the fr tau. Next, let's see how do I take care of the traction condition. See, earlier in the one-dimensional problem, what we had done as far as the traction condition is concerned, we had actually taken the two endpoints of the element of the domain, and the boundary conditions were applied only at these endpoints. Now we are talking of a two-dimensional domain where the boundary conditions are applied on edges, okay, on the boundary edges. So we have to somehow apply those conditions into our integral representation. In the 1D case it was very easy because it was at endpoints, so I could go to the corresponding load vector entry and add numbers. Here we have to do integrals over the boundary edges. That's why we will do them not at the end of our element calculations, but while we are doing the element calculations. Okay, so this is one major difference between the 1D case, that we do not wait till the end of the whole assembly process and then apply the boundary conditions, but rather we do it while we are doing our element calculations. So how are we going to do this thing? So let's take again our domain that we have. Let me also make the mesh along with it. Okay. So I may have on this edge, let's say I have fixed the u, that is u is equal to 0. Okay. On this edge I have given a constant flux, that is g is equal to some constant. On this edge I could have the flux g is equal to some, this will I'll call as constant C1, I'll call this as C2, and this edge is actually it's a flux condition with 0 value of the flux. Okay, so you see that there are distinct edges on which of the domain on which I am specifying the boundary conditions. Okay, So I am going to now identify these edges where the boundary conditions are changing. So I am going to identify two things as far as the domain is concerned, that these distinct edges where the domain profile is changing, those things we have to identify. Also we have to identify the edges where boundary conditions are changing of one type or the other type. Here in this example we will say that this is boundary edge 1, this whole edge is boundary edge 1, this whole edge is boundary edge 2, this whole edge is boundary edge 3, and this whole edge is boundary edge 4. So we have the 4 boundary edges in this particular problem. Okay, I will discuss further this issue, but let us take this particular case. Okay, so on these 4 boundary edges, now you see there are different types of boundary conditions. So what I am going to now do is, I am going to, as we had done earlier with respect to the IBC type, remember that we had talked of IBC type associated with the 2 end nodes, telling us what kind of boundary condition is applied on this end nodes. So if my IBC type is now going to be defined for the boundary edges. So I have 4, so here I will have 4, and I am going to say this IBC type for a particular edge is equal to 1, this is my choice, when I have homogeneous Dirichlet boundary conditions, that is when u is specified on the edge and u is equal to 0. This is equal to 2 when I have non-homogeneous Dirichlet boundary conditions, that is u is equal to u bar. Now in practical applications we can take displacements applied on the boundary, which can be displacement controlled problem or a temperature controlled problem, okay, where the displacement on the edge can be at most linear. Okay, so we are not going to have very fancy profiles. We will say, okay, from our implementation point of view, it could be a linear, let's say. So we will say that, so by this u bar we mean some non-zero value of u is given on the boundary. This is a given boundary condition. I will say it is 3 when it is a Neumann boundary condition with homogeneous type of boundary condition, that is G is equal to 0. So it is a homogeneous Neumann boundary condition, and it is equal to 4 when it is a Neumann boundary condition but G is equal to a non-zero value G bar. Okay, so this is my way of representing each type of boundary condition that can exist on the given boundary edge, and this number I am going to assign for each of these boundary edges. So for example, for IBC type 1, in this case IBC type for the edge 1 is actually type 1. IBC type for edge 2 is G is non-zero, so it is equal to 4. Okay. Similarly, IBC type for edge 3 is also the non-zero Neumann, so it is also 4, and IBC type for edge 4 is the 0 Neumann, so it is 3. Okay. So my first job is to identify the edges where a specific type of boundary condition is applied. Now for those edges I am going to specify what is the boundary condition type. Now once I have the boundary condition type, let's say I choose that my flux on the boundary, I am trying to solve a set of problems for which the flux on the boundary is at most linear and the applied displacement on the boundary is at most linear. So I can give the flux and the displacement as linear functions on the boundary. I can give them in terms of the x and y, or I can give in terms of the normal and tangential components. Okay. So here let's say that we are giving it in terms of x and y. So when we are giving the u and u bar and the g bar in terms as a linear in terms of x and y, so it will have 3 coefficients corresponding to the a0, a1x, a2y. Okay. So those 3 coefficients have to be given as input data for the particular boundary edge, store it, and then we are going to use it. Now the question is, okay, how do I now use this information to do my boundary integral calculation? How does one know a priori or while doing the computations that, okay, this element has an edge lying on the boundary? That information has to be generated somehow. So I'm trying to think more like a computer here. So let's say that, okay, if I go back to my previous picture, here element 1 has an edge on the second boundary, element 2 has an edge on the first boundary, element 3 has an edge on the second boundary and an edge on the third boundary, element 4 has no edges on the boundary. Similarly, element 5 has no edges on the boundary, element 6 has one edge on the boundary 1 and the other edge on the boundary 4. So this way I have for each element either one or more edges are on the boundary or none of the edges are on the boundary. That is, an element is a completely internal element when it has no edges on the boundary, or an element is a boundary element when it has at least one edge on the boundary. Okay, so we are interested in these boundary elements. How do I obtain that information? So what I do is, while we are making the mesh, we make essentially a neighborhood information for the edges of the elements. Okay, so what we do is we make this neighborhood information. So element, we call it element edge connectivity, and we'll give it a name. We'll say side underscore neighbor. Okay, and this will have, I will put it because for all the elements, that is, there are NEL elements in the mesh, and for the three sides of the element. Now how have I numbered the sides? If you remember that if I have, let's say, a generic element like this, this is the local 1 node, this is the local 2 node, this is the local 3 node, then the side with the ends as nodes, local nodes 1 and 2 is side 1 of the element. The side with ends as the local node 2 and 3 is the element side 2, and the side with ends as the local nodes 1 and 3 is the side 3 of the element. So this is how I am going to identify the edges of an element, the three edges of an element. Now if I took element 1, so for the element 1, if I go make the picture here, element 1, okay, this will have this as edge 1, this as edge 2, this as edge 3. So on the edge 1, now this edge 1 if I see, then I look at the side neighbor of element 1 for the edge 1. Side neighbor for the element 1 for the edge 1 is the side, is the boundary side 2. So then I will say the side neighbor of element 1 for the edge 1 is the boundary edge 2. I am going to, when it's a boundary edge, then I am going to assign a negative number with the number being the corresponding boundary edge. So I will give -2 as the neighbor of this element on this side. So as soon as I see -2, I know that this side lies on a boundary, and not only on the boundary, it lies on the second boundary edge. Similarly, if I look at side neighbor for the element 1 on the edge 2, this for the element 1 on edge 2, if you see here, this is the edge 2 of the element 1. Okay, this edge 2 has a neighbor as element 4 because the element 4 shares the same edge with this element. So this will be equal to 4. Side neighbor similarly for element 1 on the edge 3 is equal to, if you see, the edge 3 is this, the side neighbor is element 2. Okay. So this is the way I can create this edge connectivity information. The question is, why do I need this information? One is to identify which edge of the element of a given element is on the boundary. One, first of all, whether the element has any edge on the boundary or not. Secondly, if it has, which edges, and then which boundary segments do these edges lie on. Because for the boundary segments, we have now specified as an input data the boundary conditions. Okay, so those are available to us. So that we have to transfer to the integral on the boundary. Also, when, if you remember, we did some post-processing of the stress information in the 1D case, where we obtained this recovered stress field using information from the elements adjacent to the element, to a given element. Okay, the two elements on the other side of the two element of a given element. Same thing we can do in the 2D case also, by taking information from all the elements which are in a neighborhood of the given element of interest. So for that we need again to obtain this connectivity on the side information. Okay, so this information we create. So I mean, once we have this information, then so we do it for all the edges while we are making the mesh. Okay, and you see that by making this information, we can also immediately figure out which edges are lying, which element edges are lying on the Dirichlet boundary. Okay, and from there we can find out on which nodes or on which degrees of freedom of the domain have to be assigned values because of the essential boundary conditions specified. That is, which of these ui's in the representation of my finite element solution have to be given fixed values. Okay, so that information we'll talk about a little later. So okay, I now have this side neighbor. So now let's say that I go to element 1. This is the local 1, this is the local 2, this is the local 3. Now this element 1, I start looping over the edges, loop over 3 sides of the element. So I start looping over the 3 sides of the element, and I check if that side has a negative neighbor. Okay, if it has a negative neighbor, I check whether that negative neighbor is minus 4. Okay, why do we say that the negative neighbor has to be minus 4? Because remember, we are talking of only computing the integral on the gamma bound on the Neumann boundary of g ni tau ds, g ni tau ds. Now this we are only interested in the boundary segment where g is non-zero. Out of the Neumann boundaries, we are interested in only the boundary segments where g is non-zero. Wherever g is 0, this integral becomes 0. So I don't even have to bother about computing this integral. That's why I distinguished between the homogeneous Neumann boundary condition and the non-homogeneous Neumann boundary condition. So we are only interested if I side neighbor for the element I for the jth side is equal to minus 4. When this is there, then for that particular side I have to do this integral over the side. Okay. Now how do I do this integral over the side? We have to do this integral against the ni tau. Now we have to ask the question, which of the element shape functions are non-zero on this edge? So which of the element shape functions are non-zero on the edge? You see n3 becomes 0 all along this edge. So the only non-zero shape functions on this edge are my n1 tau and n2 tau. Okay, so n1 tau and n2 tau are the only shape functions which are non-zero on this edge, which is This is my first edge of interest. So given the edge, I can easily find out which of the shape functions of the element are non-zero on this particular edge. Okay. So I found this. Now if you look at these shape functions on this edge, they are now exactly the one-dimensional shape functions that we have studied earlier. Why? Because you see along this edge, it is a line now. Along this edge, your n1 tau is 1 at the first node, 0 at the second node. n2 tau is 1 at the second node, 0 at the first node. So they are exactly the 1D shape functions. So we can use all that we have learned with respect to the 1D integrations to do the integrations of the non-zero Neumann conditions against the shape functions on this edge. Okay, numerical integration, all those things we can do. Now what we are saying here is, let this G also be a constant. Here, as a simple case, we are taking the G to be constant on this edge. So let's say if I am talking of the element 1, then I find that the first edge of element 1 lies on a boundary which has sorry, I made a mistake in my here. The side neighbor is I'm wrong here. Side neighbor is negative. Okay, so here I have I side neighbor is -2, -1, whatever, but only when the IBC type for this neighbor, when the IBC type for this particular boundary, let's say, is equal to 4, then only I am interested in this boundary edge, otherwise I am not. So I made a mistake in transferring the data. Okay, so only when the IBC type is 4, then I am going to do the integrals on this edge. So here I find that this boundary, this edge of the element, the first edge of the element lies on the boundary edge 2. The boundary edge 2 has a IBC type which is 4, and now I can go ahead and do the integral of the given G on this edge against the shape functions which are non-zero on this edge. Okay. So how do I do it? So if I take the first element, let's say this is element 1, so I will have integral over edge 1 of the element, okay, of G, which is C1 into n1 tau ds, okay, and over edge 1 of C1 into n2 tau ds. Okay, so I have to obtain these two integrals. Now n1 tau ds and n2 tau, C1 and C1 is a constant, so I know what is the integral of the linear 1D shape function along an edge when I know the length of the edge. Okay, so I'll have to find the length of the edge. How do I find the length of the edge? Length of the edge is very simple. It is essentially square root of, if I take the first edge, it is x2 minus x1 squared plus y2 minus y1 squared. This is equal to L1. Similarly, I can find the length of all the edges of the domain, okay, of the element. So I know the length of this edge is L1 for the first edge, L2 for the second, and L3 I can find from the physical coordinates. So this integral, we have done enough of this, is simply equal to C1 into the length of the edge, okay, divided by 2. Okay, why? Because the integral of n1 and n2 is the same, and n1 plus n2 is 1. So integral of 1 along the edge is the length of the edge. So because they are the same, so this becomes L1 by 2. Similarly, this guy is also C1 L1 by 2. Remember, for the edge of the particular element. So now I have these two integrals for this element. So what do I do? So next, I have obtained f1 tau r, f2 tau r, f3 tau r. I will now obtain the same thing for the sides. okay, and then I am going to have my f1 tau so I loop over the sides, add these, compute these integrals that we have done, compute these integrals, add it to the f1 tau side, f2 tau side, f3 tau side, depending on which shape function is non-zero on this edge. So for example, the first edge I will only get to the f1 tau and f2 tau contributions, f3 tau will be 0, and other places something else will happen. So I obtain this vector after looping over all the 3 elements. Then my total f1 tau is equal to f1 tau or f2 tau or f3 tau r plus f1 tau s, f2 tau s, f3 tau s. So I have found now, essentially while I am doing the element calculations, I will do an integral over the area of the element and an integral over the edge of the element. Area integral will give me the stiffness matrix entries and the load vector entries coming out of the distributed source term, while the integral over the edges or over the sides gives me the load vector entries coming out of the non-zero Neumann boundary condition. Okay. In general, I am going to always initialize, obviously before doing the calculations in the element, I will initialize this vector to 0, I will initialize this vector to 0, I will initialize this vector to 0. After doing my integrations and so on, this vector will have some entries, this vector will have some entries, simply add them up and I am done. So now I can actually obtain all the information about the Neumann boundary conditions at the element level itself and do essentially the adding of these contributions to the element load vector in one shot. Once I have that, then I have all the information that I need as far as the Neumann boundary conditions are concerned. So the next step is that, okay, we have obtained the element stiffness matrix, element load vector. Now what do? I will have to assemble them to obtain the global stiffness matrix and load vectors. Okay. So global stiffness matrix will be K global and global load vector will be F global. So what do? So for that, again I need to construct the information which tells me where do the element degrees of freedom go to globally, that is, which global degrees of freedom do they correspond to. So remember that for the first element, for example, the local 1 corresponded to global 1, the local 2 corresponded to the global 2, the local 3 corresponded to the global 5. For element 2, the local 1 so for element 2 the local 1 corresponds to the global 5, the local 2 corresponds to global 4 and local 3 corresponds to the global 1 and so on. Okay. So I have to somehow construct this information. This information again I can do as and when I am making the mesh, because when I am making the mesh, then I can go and see, okay, my local 1 corresponds to which global node, because I am anyway storing the name of the global nodes assigned to the element. Okay. So there I can go and construct what we had done earlier as the we had constructed the degrees of freedom array or the vector IL DOFs. Okay. This is a vector for which for an element I will have a starting point of, you will see in this case, 3 into I stop करो, इसमें गड़बड़ हो रहा है.